if y'all have questions, you can feel free to ask me right off the bat. So in the talk here, I'm focusing on local, largely anthropogenic local impacts to the climate. And there's lots of other impacts to the climate, as Bruce can tell you much more about, the solar radiation, the greenhouse gases, the El Nino, La Nina weather cycles, that are more regional, volcanism, magnetic field reversals, meteorite impacts, all those can affect the climate. But we're going to flush out from the past signals and what's happening now, the effects of vegetation and soil, and rainfall, temperature, things like that. And so here on the right, you're seeing an old record going back to 800 years AD, showing increases of temperature since 1800, and so forth. And so we'll be looking mostly at the local effects of soil and vegetation. So I'm going to start off with 1904. William Bray was a forester with the Department of Agriculture. And he came here to Central Texas and did an evaluation about the forests here and how they affect the climate and the water supply. And I'll have his report in the Google Drive for you all to read, along with the other ones I'll be citing. It's really interesting because he saw a lot of things he saw in 1904 are the same things that we have a good scientific basis for now. But mostly what you hear nowadays is that, well, the trees use up the water from the aquifer, and they're a huge wildfire risk. I've got I'm the manager for 13,000 acres of preserves, and the residents nearby a lot of times go to the city council. They want us to clear the trees, because they're too much of a wildfire risk. Trees just explode, So, I've been trying to look at the scientific basis for these beliefs. Why do people think that the water gets dried up from trees? And why do they think they're a wildfire risk? So we'll be looking at that in this presentation.
Nico, let me interrupt you real quick.
Yeah.
Could you bump your volume up just a little bit?
Any better?
I think so.
Is that better? Okay. All right. So
Thank you.
Yeah, William Bray's conclusions, one being the deeper rooted trees increase the infiltration, the water going in the ground, reduces the runoff, which causes flooding to the creeks, reduces the erosion, so that have a really good impact on the climate. And then once you clear cut the forest, which you saw a lot of back in 1904, it increases the erosion of the soil, increases the flooding problems. And he also pointed out that the forest and the soils together act like a reservoir, like a giant reservoir of water. And he was also aware that a lot of people believed at that time that the forest attracted rainfall, but he didn't have a scientific basis for it. Well, now we do have some scientific basis actually indicate that forests actually do attract the rainfall. That's called the abiotic pump hypothesis. We'll be talking about that as well. So this is a diagram showing you the differences between the soil reservoir and vegetation on the left-hand side. We have bare soil or bare rock, compaction, a lot of runoff, a lot of evaporation going on. So it's pretty well demonstrated in lots of studies that forests do diminish runoff. One study by Bosch and Hauwert back in 1982 looked at 94 catchment studies. And these catchment studies is where you have a drainage basin, and all you're measuring is the runoff coming off that basin. So you can have one basin you clear all the trees on it, and the other one where you have the trees, and you can compare how does vegetation affect the runoff. And the second study, the Farley and Jackson studies, they looked at 26 catchment sites, and they all pretty much agree that once you have forests, you don't have as much runoff going to the creeks. The difference is they look at it and they see the trees stealing the water yield for the creeks. The lack of runoff is assumed to be a bad thing that's causing water shortages, causing the creeks not to flow as much. But the reality here in Central Texas particularly is our creeks are mostly base flow from spring flow that keeps them flowing. And so the waters that you see going during during a storm event going to the creek is more likely to contribute to the flooding problems, and not to make the sustained spring flow in the creeks. So what they see as being a bad thing is actually a good thing. The trees are taking the runoff, and that's actually a good thing. Ellison et al. 2017, this is probably the best paper all about what I'm talking about today. So I'll make sure to have that one available. And he notes that removing trees, you go remove the trees, you're increasing the soil compaction, soil erosion, reducing the transpiration infiltration, and promoting floods. So he sees the trees as being a good thing. So why do the trees enhance infiltration? A number of studies pretty consistently show that the roots of the trees act as macropores to transmit the water into the soil and into the aquifer below it. And the picture there on the top is showing this large ring infiltrometer that Adrian Minley used. It's like 10-foot diameter. He pumps it full of water, and you see how well the ground takes the water over time. And the graph in front of you is showing you the fastest infiltration times are at the bottom. So the juniper is here in the red circle. These are an area that just has juniper roots. Most of the rest of the sites are places where there's sinkholes that are filled with soil, mostly what he's focusing on. But actually some of the fastest infiltration was in areas that had juniper roots in them, and open solution cavities that are like, pipes in the rocks and sinkholes. So pretty consistently people see that where you have trees, you have more infiltration into the ground. The pioneers looked at it kind of differently. They try to keep as much water at the surface. So a lot of the ranches I go look at, I'll see 3 or 4 large full sinkholes that were plugged at the bottom to provide water for livestock and cattle. And the pioneers and ranchers plug caves for lots of other reasons too, including they didn't want their livestock to fall into pits. They wanted to get rid of their trash. And for other reasons, they plugged the sinkholes. And so for us to restore a land like the one you see on the left-hand side where the water is ponding because that sinkhole's plugged with 4 feet of water across 200 feet, a pool, we dig out the dirt and restore the sinkhole so it takes all the water in. So for us, a good thing is where the ground takes all the runoff, where it would naturally go, and not that we plugged everything so that it goes to the creeks. That's going to increase your flooding. So another thing I want to look at is the Blanco River. And here on the left-hand side is the mouth of Halifax Creek into the Blanco River, which we did dye tracing in 2009 and pretty demonstrated that this area is what sustains Barton Springs during the drought. It's the Blanco River, 20 miles away, that keeps Barton Springs flowing. Now in the 1890s, they saw this spot where there's a cave that took all the flow of the Blanco River, and it was a problem for the pioneers because they had a mill in the Kyle area and they wanted that mill to keep turning, but this cave kept taking all the water, so they made a concerted effort in the 1890s to plug it up. And there were many sites across the whole area where the caves were plugged up, and of course I wonder what effect that had on flooding that you saw in 2013 in the Blanco River and in the other local creeks. So in around 2000, I initiated the first kind of climate research site in South Austin to try to directly measure all the components of rainfall that come down in the area. And this site is located on the J17 research site, just south of the Lady Bird Johnson Wildfire Center. And before then, based on pretty not really good science, the development during the 1980s and 90s was based on the assumption that only less than 1% of rainfall recharged the aquifer. Really low number. It's sort of like the parking lot at Barton Creek Mall or Clay. 1% didn't match anything else you saw in the whole rest of the world on cave areas, so it didn't make sense. So I came in with instrumentation to measure the rainfall and components like the runoff. We'll talk about the runoff first. So this device on the right-hand side measures the runoff. It's called a flume, and it continuously measures the runoff In this particular case, in the grove of trees in the left-hand side, there's a sinkhole there that takes all the runoff from this site. So it's a closed internal drainage basin, basically. Normally that runoff would go to the creeks, but it was kind of a closed system that allowed me to study all the components of rainfall. Okay, so we also put a tower up to measure the evapotranspiration. And evaporation is the conversion of the liquid water to gas. In the process, it cools off. And the transpiration is the water used by plants for cooling. They're taking their nutrients in there. They're using the water in their structures. And they also are taking in carbon dioxide from the atmosphere. With this tower, I can measure it over a 1 mile radius, the flux of water. These towers are cool because they can also measure the carbon flux. So they're pretty useful. And this is the way to measure the actual evapotranspiration. Other people reference evapotranspiration. They're measuring it with pans of water. And that's kind of appropriate if you have a lake of water, or if you're irrigating crops, you have no shortage of water. Whereas in this area, when the soils become dry, you don't have as much water in the system. So that's actual evaporation versus potential evaporation, which has no limit. And I took out the slide to show most of the results of this because it takes a little while. But basically, what we saw, instead of less than 1% of rainfall recharging the aquifer, we saw about 28%, I'm sorry, of the rainfall recharge the aquifer in this area. And we also saw that I compiled the differences with other people's climate towers, where they were measuring the difference between forested areas and grasslands. And there really wasn't that much of a difference between the two as far as how much evapotranspiration occurred. During the drought, from the compilation I did, it tended that the grass areas would lose more water than the forested areas would. And you can look at the study down below to get more information on this study, which will be in the folder. So is high evaporation transpiration bad? As I mentioned to you, the process of evaporating, transpiring cools. A single tree can produce the equivalent of 2 home air conditioning units. So if you like a cooler environment as opposed to being really hot, evaporation, transpiration is good. During heavy rainfall conditions, whatever transpiration, evaporation, soil moisture storage, and aquifer storage that occurs is going to reduce the downstream flooding. So that's good. Now, in my research, evaporation is really low during rain events because the humidity is really high. But whatever transpiration can occur is going to be a good thing during those conditions. And then the evaporation, transpiration that's lost to the atmosphere actually produces rainfall downwind. It's estimated about 61% to 40% of the rainfall we have is derived from land surface, from vegetation, from soils, from marshes, lakes, rivers, and the rest of it is the other half basically is coming from the coast. So we're seeing more. Traditionally, we thought that all our water comes from the coastal water, but we're seeing more and more is actually terrestrial derived. The low pressure from the rising water flux creates a low pressure system that's hypotheses brought in rainfall. So it's not just that we have ET going in the air that's going somewhere downwind, but the rising flux is also dragging in water from the coast, bringing it in. The opposite of that is what happens in the high plains of Texas, and that's where you're seeing hot, dry air rising. It's creating these things we're going to talk about called anticyclones that are high pressure systems that try to kind of force the rain fronts away, so that they cause prolonged droughts because they're forcing the rains away from that area. So evapotranspiration actually is not a bad thing after all. Now we're going to talk about the cooling effects of vegetation, the contrast between the bare soil, which is hot, and the cool soil is cool. We talked about some of the data that shows that that's the case. And so here's albedo. Let me introduce albedo very quickly, and that's where the sun radiation is coming in. Where the light surface is, it tends to reflect the albedo back, the radiation, and tends to be cooler. Places like forests that are dark, based on albedo alone, should be absorbing the radiation and should be warm. The models based on mostly on albedo, will tell you that the more forest you have, the hotter it's going to be. And then if you remove the trees, it'll be nice and cool. But we don't see that in reality, and let's look at why. A lot of people looked at the models about, you know, of the cooling of the surface, looked at the Sahara Desert, where the sands have a relatively high albedo. They should be reflecting the sun's rays. The radiation should be cool, but you see the opposite. It's very hot there. And anyone who's come and measured the albedo notices the vegetated areas are a lot cooler than the bare areas, which have high albedo. It's opposite of what you expect. So we call that the albedo anomaly. And the reason for that is something, it's not that albedo doesn't occur, that something else is more dominant than the albedo in affecting the temperature. So here's some measurements what people took comparing grasslands to forests. And in each case, they saw that where you have forest, you have a lot cooler temperatures, a lot more stable temperatures than in grasslands. It can be very hot and dry. And you can intuitively observe this by going out into grass areas versus being in the warm forest here in Central Texas. And we're intending to get some actual measurements like they did in Central Texas of these different terrains to be able to compare the differences between them. So does the land surface moisture promote local rainfall? So one model that was done in '82 by Shukla and Mintz was a worldwide model, and they simulated two conditions. One, we had a wet, moist soil and vegetative surface, and another where you had no soil, no vegetation, and as a result, the moisture was low, but you did have moisture coming off the oceans. And what they saw that applies to Texas is things that we had a vegetative moist surface with soil, things were cooler, there's more rainfall. In the case of Texas, they saw the simulated temperatures in the vegetated areas were 68 to 70 degrees Fahrenheit, as opposed to the dry areas where it didn't have vegetation, where they got up to 113 degrees in July. The rainfall in July was 4 to 5 centimeters more per day in the vegetated model than in the unvegetated model. So there's a model showing the differences between them. Milan studied the Mediterranean area in Europe, in the Mediterranean, and made a correlation between the floods they had in Europe and the droughts they had in the Mediterranean. And he said it all had to do with the vegetation, the marshes, the soils that are able to provide enough moisture for the storm fronts to create. In the case where you didn't have enough vegetation from the deforestation that was occurring in the area, what you saw is that the storms tried to build up, but they couldn't quite, and then they would build up and back up, and then eventually you'd have this big flood hit Europe as a result. So this is kind of an interesting report on where he showed the effects of the vegetation in the Mediterranean and Europe. In the United States, in the central United States, a couple of studies found that the soil moisture was a better predictor in the springtime for droughts in the summer based on the soil moisture and the vegetation. Then the regional El Nino oscillation and other more regional wide patterns, that the local soil moisture was a better predictor whether you can have droughts or not. And that indicates that you are getting a component of your rainfall from the soils and vegetation. So do forests actually attract rainfall? And for several reasons, there's pretty good evidence for that. One thing, the leaf surface area in the forest can have a lot more surface areas than an area on an ocean. And that seems to be a factor in how you can generate a lot of water through transpiration. That the rising cool water fluxes creates a low pressure system that actually draws in the moist wind currents from the coast. And this is from Makariv and Goshev in 2009. As I mentioned to you before, in places like the high plains of Texas, Namias noticed that you have these anticyclones that form in warm regions when the ground is hot. Sinking dry, warm air goes down, and it creates a high pressure system that keeps out the rain fronts. And there's also a role that the biological aerosols play in enhancing, causing the precipitation of rainfall. Some sediment can actually prevent it from happening or retard the rainfall, aerosols. And you tend to get those in the dry, dust-blown environments. So Makariva and Gorshev did an analysis of many different places across the world to show the distance to the coast is not a defining factor, or the prevailing winds, and that the big factor had to do with the vegetation. So on the right-hand side, you're looking at the amount of rainfall across two transects, number 4, which goes across North America, number 5, which is East Asia. And the filled-in circles indicate where they're vegetated areas, and the hollow ones are where they're not vegetated areas. So the difference between North America and East Asia, they have much less rainfall there. It's because they have less vegetation. And in this paper, they look at many different comparison cases to show that it's not the distance from the coast, but it has to do with how much vegetation you have in that area, whether or not you'll get rainfall. So in history, you can look back, and Redmond and Hughes did a pretty good analysis across the world where deforestation was directly tied to the erosion, loss of soil moisture that's available, directly impacted the ecosystems, the habitat in those areas. Once the soils were lost, the native trees couldn't recover through natural forest succession. And so people were left with a degraded environment. And another study by Jenny also showed that cores worldwide and pollen analyses showed that when you had deforestation was associated with a lot of sediment deposition across the area. So you lost your sediment on the upland areas once you deforested these areas. So here's some cases where deforestation and soil loss was attributed to climate change. In one case is in the Sahara region. Ethiopia was forested with about 65% trees, 35% grass, twice the modern precipitation about 3 million years ago. And then you started seeing human artifacts appearing 2 million years ago. The landscape changed to where it's 50% grass. The rainfall is diminishing. And Wright concluded the Sahara Desert is there because people, through deforestation, used to be a forested area, cleared the trees, the rainfall stopped coming, the monsoon stopped coming, and that's what transformed it into the desert we know today. So it's kind of an interesting analysis of the Sahara Desert. In Greece, in 360 BC, Plato wrote that over 9,000 years, Greece never really experienced significant soil loss until they started deforesting the area. And as a result, the forests were gone, the soils eroded away, the rainfall diminished, and the springs stopped flowing in that area. So this is an interesting case study in Greece, where it used to be forested and was cleared, and now it's a whole different character. So in modern Greece, like many other places across the world, transformed from a forested region to this maquis shrub vegetation, which is chaparral vegetation. Now it has countrywide wildfire risks. It's a national disaster, like in 2007 and 2018, where you have countrywide wildfires because it's so hot and dry. The vegetation is completely suited for wildfires. The trees would tend to keep the moisture that would prevent wildfires, but those are gone now. Some other studies that related rainfall to deforestation in South Florida, they saw that with the deforestation that occurred over 93 years, they saw an 11% decrease in rainfall and an increase in temperature. And in Malawi, which is in Africa, in the last 10 years, they experienced a 10% deforestation across the country that corresponded to a 9% decrease in rainfall during that time. So in Texas, this is a picture I took of High Plains. They're near Hauwert Yeah, there we go. So the vegetation is pretty sparse in the high plains. There's a high pressure warm cell that tends to build there that tends to deflect rainfall from the area, and sometimes even central Texas in that area. In the Dust Bowl, which is higher up in the Great Plains, after World War II, there's extensive change of the landscape to promote farming in the Great Plains. And after a decade of extensively changing the landscape in that area for agriculture, in 1930 they saw a pretty severe drought, and most people associate the drought with the landscape changes they made in the Great Plains. You know, so another case where the drought seems to be associated with land changes, and probably the loss of soil moisture is what they attributed to. So here in Texas, Brad Wilcox did a study showing that the apex of the livestock was during the 1940s, and after that time, we saw regrowth of the forests during that time. And he also noted that as opposed to people that would expect that the creeks would dry up with the growth of trees, you know, because how they suck water, right? He actually saw that the stream flows increased during that period. Since that time, they've been increasing. In the Guadalupe River, the Frio River, the Nueces, the Llano River. He didn't see an increase in rainfall, probably because his rain gauge was in San Antonio. But other studies who looked at rainfall and flow in the area saw that rainfall increased about 13% since the 1940s drought. Barton Springs increased about 86%. You know, so they actually saw again the increasing stream flow, spring flow, rainfall since the 1940s with the regrowth of trees during that time. So conclusion, so I'm ending up my talk here is to conclude what we talked about, that a large portion of the climate change is a result of local land use changes, particularly deforestation. You're losing the water, the moisture. You need that to enhance the rains. The forests and soils work together to create a large water reservoir, and evaporating water flux may attract rain. And that if the forests were cleared, the regions can be expected to be at least 20 to 45 degrees Fahrenheit warmer and get less rainfall during the time. So we'll experience more droughts as a result of deforestation. And we'll also make a transformation to drier grasslands that are more susceptible to wildfires and more extreme desertification. And again, more studies needed to look at this in detail and how it applies to Central Texas. And that's the end of my presentation. I'm going to leave you with this slide, which is a exhibit they had there in Austria, where they put a forest in the stadium, you know, like go trees, right? And here's a quote from William Bray: considering all the interests dependent upon water supply of the region, there would seem to be little ground for opposing the policy of maintaining and where necessary establishing forest cover upon these arid hills, talking about Central Texas. And that's the end of my presentation. You want to see any?
You're just going to go ahead and go to Jim, and we'll get all the questions at the end.
Okay, that's good. Let me clear out let me stop sharing here.
Okay, we got you, Jim. Take off. Introduce yourself first, too. Please, sir. And unmute yourself, too, maybe. Yes, unmute yourself.
Okay, there we go.
There you
Can you hear me now? Yeah.
Yes, sir. Thank you. All right.
The transition, I know. Let me see. I want to make sure that my slides are advancing. Yeah, they're not advancing. I have this trouble every time. We just finished with a 7-part series on forest restoration, and I will introduce myself and then kind of fiddle with this. Once it gets going, it works fine. So my name is Jim O'Donnell. I'm a biologist with the Balcones Canyon Land Preserve. And I served in the biological advisory team in the 1980s that came up with the design and biological needs for the preserve system. The Balcones Canyon Land Preserve came enacted in 1996, and I also spend a lot of time monitoring golden cheek warblers and black-capped vireos across the preserve. I also grew up in the Bull Creek watershed, so I used to wander these hills as a kid, and now I get to do it professionally, so it's a real treat for me. I'm still working on trying to advance these slides, so give me a second. There's always this little technical glitch here at the beginning, so let me...
I saw you.
There we
There
go.
you go.
Oh, I got it. Okay.
All right.
All right, yay. All right, thank you. So this is a map of the Balcones Canyon Land Preserve System, and the area that I do most of my restoration work is down here on the Vireo Preserve. I was able to get this land set aside back in the late 80s and 1989. Janet Pogue, who set aside Wild Basin, and I teamed up to get the Vireo Preserve set aside. I'm also doing restoration work on a larger property now, Double J and T. So right now we're actively doing restoration work on about 2,000 acres. And so the Vireo Preserve supports black-capped vireo habitat and golden cheek warbler habitat. Some of this property, as you'll see here in a second, has been degraded for over 80 years. So we're trying to restore that property, and lessons learned here, we apply to other places. Kind of, leaping off of what Nico was talking about, William Bray, a forester, took this photograph very close to the Vireo Preserve looking north, and he talked about it was almost an impenetrable growth of juniper and other hardwood species, great soil, that kind of thing. And this is 1904. He turns his camera during this time period to show the clearing of juniper. There was a culture at the time, cedar chopping, which really began in the 1860s. By the time the railroad came in to Austin in the 1870s, we were trucking out and clear cutting this area pretty extensively, to the point where there's about 250,000 juniper trees shipped out of this area during that time period in the late 1880s. So as you can well see, you lose all the tree cover there, and you've got some real erosion issues. And that's kind of what we're going to be addressing today, is how to fix this stuff. One of the slides that Nico sent my way is real interesting, showing, back in the early 1900s, if you see common fords there, which we've all probably walked around in, and let's see if my cursor works up here. Here's common fords here. And just, notice all the clearing that was taking place, in the early 1900s here, and all that sediment washing down into the river here. And we've got quite a silt buildup even as early as 1918. And there's a spring, Santa Monica Springs, just down the way, that totally clogged up by all of this silt. William Bray also shows, and you can see the photograph of this area here, the clear cutting that took place back in the 1940s or just earlier. And you can see these wide swaths of land that were just completely clear cut. Now you can well imagine what water does in a 10-inch rainstorm down this hillside, and we still see this type of stuff today. And I think that's a picture here of what it looks like today. So you can well imagine that if we hadn't done the clear cutting, it wouldn't be looking like this. And unfortunately, when I served on the biological advisory team, we had recommended 125,000 acres in western Travis County to protect golden cheek warblers and black-capped vireos, and 62 cave systems through western Travis County. We ended up with 30. When science meets politics, it always doesn't go well for science. So we ended up with a little over 30,000 acres. And we have some great prime habitats. We have some really nice stuff. But because of past land use, we also have areas that look like this. And given the fact that we have 30,000 acres and not 125,000 acres, there's nothing throwaway here. So everything needs to be moving towards black-capped vireo habitat or golden cheek warbler habitat to comply with our permit. So Nico summarized this. I'll just hit on it real quick that William Bray, after doing work in the area, found that forests indeed do build soils. They protect against erosion, and they act as a sponge to capture water. This is one of our prime habitat. We kind of evaluate habitat on the BCP as areas that need to be restored, like the picture you saw before. Areas that are sort of in transition, you know, they're enhanced areas. They're coming back, and then we have we protect habitat like this, which is prime habitat. Here we have an example of golden cheek warbler habitat along with the Barton Spring. The Jollyville Plateau salamander. The salamander requires clean, clear, and consistent clean water, so any sort of pollutant in the area would do away with them. So we do have these wonderful pristine areas as well. This is an area that was probably cleared back in the 1940s or pre-1940s, and it kind of shows what a lot of our hillsides look like. It's really difficult when people clear hillsides, and I see this all the time out in the hill country, to restore that, because you lose your topsoil, and then it just kind of goes downhill from there, literally. But you can see this one little juniper tree, and juniper is a great stabilizer on these hillsides. What we did here is we took some soil samples, and you can see the one on the left there is underneath the juniper mock there, and then the one out in the open that doesn't have as much carbon in it, the lighter colored one, is from the grass area that surrounds that. We did a little soil analysis for carbon, and we found that the juniper had about 10% carbon, and the bunch grass was only about 2%. So I'll be talking about the soil sponge here in just a second. That's what we're trying to create on some of these areas to rehydrate the landscape. But soil, the carbon in the soil, it captures and stores more rainfall when it rains. You want to be able to hold that rainfall. It's less vulnerable to erosion and stores and supplies more nutrients, increasing the fertility of the land as well. This is a little scoop right underneath one of those juniper trees. You can see how rich that soil is. And then you go a few feet out there into a caliche area and you've lost that fertility. One of the things I love, and this is from USDA, is that for each 1% of organic matter that we work into this soil, has the potential of holding 27,000 gallons of water per acre. So it kind of gives you an idea that if we treat our soils right and rebuild our soils and add plant communities back in here, we can capture and hold a lot of water. This is something we see all too often, and neighbors around our preserves or just out in the hill country in general. And this is the drying out of landscape. What you're doing here is you're releasing CO2. We normally think of CO2 just being released by cars and factories and that kind of thing. But clear cutting that, burning it, biocides, and overgrazing all release CO2 from that soil. It just literally oxidizes and we lose it. And then from that, we don't have the organic matter because it gets washed away, it gets drier, hotter, that kind of thing. This is one day I was out at the Vireo Reserve. It was 104 degrees. So I thought, well, let me take some soil temperatures here to sort of illustrate what Nico was talking about. And the open caliche area is 104 degrees, soil temperature 120 degrees. I walked just off the road here into a little woodland canopy, and this is not like a forest. This is just sort of a protected little area under juniper, and it was about 87 degrees and just a few feet away. Now, it makes you wonder where you want to sit, eat your lunch. You know, it's not going to be out there on that caliche. This is something that Nico was talking about, but really bears repeating. Bare soil, which there's a lot of out there. And so you have bare soils. If we have a 10-inch rainfall, we have a 5-inch rainfall. it doesn't really matter because all that rain hits that compacted soil, runs off, and we lose all that moisture. And then when you have hot temperatures like that, with pollution and haze, it just sort of, sends that heat right back down to the surface. And here they have a soil temperature of 140 degrees, where if you have the carbon sponge, and we'll be talking about the carbon sponge here in a second, that holds the rainfall, keeps the temperatures down to about 70 degrees in a woodland area. And as we were talking about, or Nico was talking about earlier, that the thing that creates clouds and rainfall is either ice particles, salt particles, or microorganic particles like bacteria. And you can see bacteria coming off of these trees, and then you have cloud cover. The albedo from the cloud cover, reflects the heat back up, and you have a cooling system. This is kind of what I deal with a lot. So I deal in the areas that need to be restored. And again, like I say, nothing's throwaway out there. We need to kind of restore all of these areas that are in this kind of shape. So one way to illustrate this compacted soil, lifeless soil, is get a pie dish, put some flour in it, and the flour represents compacted soil. And in compaction, there's no space for air or water. You don't have any plant cover, all right? There's nothing there, so you have high albedo, so it's going to be hot. You pour water on it. Here's our rainfall. Very poor drainage, okay? It evaporates off, and then what is there runs off. You lose your topsoil sediment, and you start making head cuts and rills, and you can see even a little bit of wind erosion on the side. I actually did this outside on a windy day, and you can see the wind erosion here of sediment blowing. And that's what we have a lot of. And then on top of that, all of this running down in here is the dirty water that's coming off of the compacted soil. Now, if you have life in your soil, which is created here with the yeast and bread, you have porous spaces. So soil aggregates are held together by carbon glues and glomalin. Glomalin, by the way, was just discovered in 1996 by a scientist named Sarah Wright. And glomalin actually comes off of mycorrhizal fungus, or arbuscular mycorrhizal fungus, and produces it. And that's one of the things that attaches to juniper roots to extend the root system out through mycorrhizal fungus. And in that space, healthy soil has about 66% space. Well, what's in that space? Well, water and nutrients then can get down into that space. You have a downward movement of water and nutrients. And then once it hits the hard pan or the bedrock, it moves out from there. And that's where springs are created. So we did this out on the Vireo Preserve, and this was a degraded piece of landscape, caliche, and this is right above an old growth spot for woodland for golden cheek warblers. And so what we did with this spot, it's a couple of acres, and so we added a bunch of biodiversity, massive planting and seeding here. We put in surface mulch and plants on here, organic matter. We put a lot of organic matter on this to help the soil sponge. And we did a little earthwork and to capture and spread water in this system here. And you can see this is a springtime shot of this. And this is in October when we first did this project, it was barren. This is another project that I worked on out on Double J about 5 years ago. And so in February, you can see this is kind of typical of that bench type, the balconies on the balconies Kenny Land Preserve. And it's pretty much stunted juniper and dominita. That's your diversity. So we put in a couple of water features in here to collect water because water was pouring down from the hilltop above this area. We had seeded it and put mulch and stuff down and just all washed off. So we had to capture that water. And this is August of all things. And 2016. And I'm working in this area now with this rather large restoration project. And it's so wooded. I tried to take a picture of it and you just see these, you can't see into it anymore. And it's simply, and it was neglected. I mean, I was not coming in here watering it during this time period. We did this project in 2016 and didn't come back until this year. And there's frogs in there, you know. So back at the Vireo Preserve here, 2014, this area has been barren since the earliest aerial photographs we have in 1940. We nicknamed the dead zone. You can see the road that the guys are walking on there. So what we did is we diverted water off of that road with some small bioswales on contour, directed the runoff from the dirt road into the bioswales, sheet mulched this area, which is just putting compost and some mulch. You need the nitrogen source to kind of break down the carbon, and which is where animals play a huge role in the system. We need that nitrogen. We need those droppings, and then we planted and seeded this area, and you can see, you know, this is 2 years later, and then it just keeps getting better. We were diverting that water, and now that it has water in the system, water was the limiting factor here. And so once we brought the water in, the whole thing changed. So what is a bioswale or a berm and swale? We use these to sort of jumpstart areas that have been degraded for a long time. So to be a candidate for a bioswale, we don't do these everywhere. I would never do it in a woodland area. These are areas that are just caliche that are going downhill. You know, environment's never static. It's either improving, regenerating, changing, or it's going downhill. And so where we're putting these, we're seeing that the hillsides are eroding even more, and we need to do something in there to sort of change the direction here. So the idea here is we cut these on contour. We have a little bit of a berm. The berm is, you know, right here. And so water comes in on these. Usually they're about 8 feet wide on the swale and 8 to 10 feet wide on the berm. We heavily plant these berms, water that comes down here, and literally we capture thousands of gallons of water in there. Instead of running off down the hillside, causing damage down the way, it soaks into the landscape. And as a result, we have dramatic changes quickly. We certainly didn't make this up. It's being done all over the world. One of the more famous ones or restoration sites is the Loose Plateau in China. John D. Liu has documented this, so he's a great person to Google, and he documents a lot of restoration projects across the world. This was the breadbasket of China that had been degraded over time, and it was the foundation. I mean, that's where Chinese civilization started, and they have revegetated and restored their property or their area. This is on the scale the size of Belgium. That's how big this project is. This is a project on the Vireo Preserve. We use a laser leveler to make sure that everything's on contour. The reason for contour is we want the water to be captured, spread, and sink. We don't want it running off somewhere. You can see how degraded it is, and this was a lot of sheet erosion kind of running down through here. We contracted with a guy who does this work, and he does these berms and swales. And what's really interesting is the Edwards Aquifer Authority is beginning to experiment with different types of land restoration that gets away from the cutting and the burning and the herbiciding approach to Texas land management, and experimenting with regenerative type land management. And they have 150 acres down by San Antonio that they're doing this work, and we're beginning to collaborate with them. Pete here, who's digging this, also works down there. And so it's kind of an exciting future on that. So after he dug the berms and swales here, we brought a lot of volunteers, and this is what's great, is working with volunteers. It's a great teaching opportunity. And they planted trees out here on the berms and swales, a lot of teaching moments here. We taught people how to plant trees and taught them about the system here. And this is, we did this in October 2019. This was the summer of 2020. You can see how fast this is revegetating already. It's just, you know, it's just taking off. There's stuff coming up that we didn't seed that must have been in the seed bank that's springing up all over the place because, again, all that water, and we've estimated about 2,000 to 3,000 gallons of water in these 100-foot ones here, and it just soaks right into those berms. We capture water any way we can on these hillsides, and rock berms, we have a lot of rocks. And what's really cool about this, and this was spring of 2020, and then in September of 2020 after a rain, the rainfall stays, it's gone, that water's gone within a couple of hours. It soaks right into the berms. But what's really neat about this thing and so exciting is there didn't used to be any wildlife in this area. You'd walk through here and it's quiet. And now you go through there and there's insects, there's spiders, there's birds sitting on the trees and the cages for stuff. And it's just an amazing transformation. And I'll just kind of run through these quickly because I know I'm short on time here, but this is another area that was an eyesore for me for a long time. So you think, well, what are the steps? What do I think about when I'm looking at this? And the first thing is this caliche, and caliche is just the mineral matter. Soil is made up of sand, silt, and clay, and organic matter. This is missing the organic matter. And it's got a lot of clay in it too. And so we needed to aerate this, and I literally had volunteers with picks opening that soil up a little bit. And then we had to slow down the runoff from the above slope because whatever we do down there and a heavy rain would wash it away. So we had to slow that down. We put rock berms and logs to capture water. We sheet mulch this area. Sheet mulch, again, is just throwing organic matter with some compost in there. We make our own compost, so that's kind of cool. And we seed and plant this for a west-facing slope. That's why this is so harsh here, is because aspect is always very important. If you're planting something that's going to have that southwest-facing slope in the summertime, they better be some hardy guys. So I don't mind things like baccharis and other fast-growing plants in here because it opens up the soil. This is about a year later or a couple of years later. And it opens up the soil and provides shade for other things that are coming up underneath it. And then I harvest this baccharis for organic matter. And so that I'll drop it, chop and drop it on place or use it in other restoration sites. And it's just sort of my crop, so to speak, to kind of help with other restoration projects. And this is just a couple of years later. See the humic layer that had developed in the dead zone there. That's the caliche. And this is what we developed in that plot. And you can see a plant here with the roots going down and the subsoil here getting some more organic matter. But there's about 3 inches of humus, which is a stable carbon. Humus is about 60% carbon. This is stable and it's growing. There's all sorts of things growing in there now. It's such an easy fix. That's the thing. This is easy to do. I basically did this with leaves I picked up out of the neighborhood in our neighborhood. And so the big project we're working on right now is at a place called Double J&T. This is one of those caliche shelves. This project goes for half a mile. I mean, you just wander, you just keep walking. And we started this in December. And this is, of course, what it looked like before. And you can see the sheet erosion coming down, a real problem here. And it was just getting worse. Typical of stuff we see out in the hill country all the time, though. This is, you know, we sent that rover to Mars, but we've got some of that stuff here. You know, there's life here. So, you know, I guess that's something. So we had Pete again digging these things, berm and swale, because every time we planted here or did something here, it got washed away. So we needed to capture that rainwater. So we did that. We get a lot of this mulch and stuff from development sites or shaded fuel breaks. So this again was in December. And we got all this mulch on there. Now it's time to plant this, and man, we're going to heavily plant this thing. And so it just goes on and on and on. And today when I was out there working, this is one of the sections here. It's hard to capture this whole thing, but we've got almost 300 trees planted out there now since December. And now I'm heavily seeding these areas of wildflowers and getting the soil going and all of that. We have master naturalists. One of the greatest things with this restoration work is all the work with volunteers. And I invite you guys, anybody who's watching, as soon as we can get people out there, I want you to come out and see some of this restoration work, especially at Double J, because it's just, you can really be spread out there. So we have master naturalists who oftentimes work with us. One rock berms. I won't go into too much detail here, but this was an area here that was once forested. When they cut the trees in the 1950s, the Texas red oaks that were there suffered heavily from that because this is on a southwest facing slope. Most of those guys died, and so now we're trying to rehabilitate the area by slowing and capturing water down the slope here. And we have in here are legumes and sumacs that we're planting now, trying to condition the soil, get the soil life going, and then we'll be putting things, oaks and things like that once we have more shade. And so we also do terrace work on some of these areas that have been washed away by heavy storms and stuff and capture water. We do work down in the woodlands sometimes, and so this is an area that's above some springs that we capture water to have it to soak in, and the spring just down below this site has not dried up in years. I think, I'm trying to remember, I don't think it even dried up in the 2000, anyway, it's been years since it's perennials now than it didn't used to be. We also put check dams in, doing a little beaver action here. It slows up some of the water that comes down these creeks, and it's not that it keeps the water from going, it just slows it up. And just a reminder, this is a decade of ecosystem restoration by the UN, so please come out and join us as soon as you can. I'd love to get as many people out and get people trained up and doing a project for us. But so that's all I've got.